Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so the problem we have here is we have four wires that intersect. Four wires, and we're told that they are very long compared to the square that they form, or the rectangle here. And that just means that they continue on outside of what we care about for this problem. So we have these four wires that make this square, and all these sides are the same. We are given their distances, d, and we're given currents here. I'm sorry, that one goes the other way. So we're given the direction of the currents in each wire. So we have, up here we have I2 current, we have I3 here, we have I4 down here. And then here we have I1. So I1, 2, 3, and 4. We are given I2, 3, and 4. We need to find I1. So the left-hand wire here we need to find. And the other thing we're told here is at the center, we have a magnetic field. A net magnetic field. Or an overall magnetic field. Which is at the center, the exact center of this square. So we need to find this current here, I1. And we have magnetic field, and we have some distances, and we have currents. So that means we're probably going to use our equation for magnetic field. B is equal to mu naught times the current divided by 2 pi r. So two things we'll have to figure out here: what our current is and what our distance is. So we have the length of each side of this square, and we're told that this magnetic field is in the center of the square, which, because these are all the same length, it's at the midpoint for all of them. That's the distance from the wire for each case. So we're going to have four separate cases contributing to this magnetic field here, and each one is at a distance of d over 2, so half of the length of d. So our distance here is d you have d divided by 2. And we have this happen 4 times, but it's the same magnetic field in all 4 cases, just different currents, and it'll be the same distance. So what happens here is we have this magnetic field has contributions from all 4 wires. Also, one thing we can notice as we rewrite this equation is that this 2 here, this 1/2 for the d, will cancel with the 2 from the 2 pi. So if b stays the same and the distance stays the same, the only other changing variable we have is the current. So all 4 currents will play a factor here. We'll have current 1. Now this will be plus or minus, but we'll have to determine what that is based on the direction. That's why I'm not writing it in right now. I'll save spaces for us to figure out which way it's going. 3 and I4. This is all multiplied by mu naught in the numerator. And then we have pi times d in the denominator, which is the distance. Now you could go through and you could do this equation here, the original equation, 4 times, and then just add or subtract depending on if it's positive or negative. But this way is a little bit more time efficient. This is the same thing because B and D stay the same. This is the same thing but in a shorter way. So let's start with I1 because I1 is what we want to solve. Let's make that positive. That's what we want to solve for. So we have current going down, so thumb down, fingers will curl underneath and back around top. Which means at our point B here, it will be coming up from underneath and pushing it out of the page. So I1 points out of the page. So we'll make that positive. So out of the page is positive. Now for D1, thumb pointing to the right, fingers curl around over top and back underneath. Which means that's into the page. So I2 will be negative. So we have our positive I1 minus I2, because that's going to have a magnetic field in the opposite direction as I1, so we'll subtract that portion. For I3, thumb down, fingers curl around over top and back under. Which means that at our point for B, it will be going into the page. Which means I3 is also negative. One more time, we have I4, thumb pointing to the right, fingers curl up and over, and then back underneath. Which means that at point B, it will also be pointing into the page. Which means 4 is also negative. So now we have all of these numbers here. So we can add all 3 of these together and subtract them from I1. So we just have one big negative I number now. You know what? Let's do it like this so we can leave that up there. So I2 through 4 now becomes, we can call it, we'll call it IC. That's I2, our I2 is negative. So we can keep this, we can make this a plus, and then have negative I2. So we can have our positive I1 plus a negative number. Minus I2. So minus I2, or you can add all these up and then just put a negative number in front of it. So our IC here, this conglomerate of all 3 of these, will be a negative number. Subtract that from I1. So that's determined from the right-hand rule and just adding the directions for it. So now we want to find I1, which we can rewrite this equation now, once again, as the magnetic field is equal to mu naught multiplied by our current one that we want to solve for minus IC. And all of this divided by pi d. Okay, so we want to solve for I1, so we're going to have to do a little bit of algebra here. Rearranging this equation. Move everything but the current portions. So I1 minus IC. Move everything on this side over to that side. We have our B in the numerator. To move mu over, we have to divide both sides by mu naught. And to move pi d over, we have to multiply both sides. So we have b times pi times d divided by mu naught. Now this is equal to our conglomerate current here, our sum of three different currents minus the current we're looking for. So we can move that IC over to the other side by adding it to both sides. So now we have the current we're looking for. Current I1 is equal to magnetic field times pi times the distance, that's the length of each of these wires, divided by mu naught plus the sum of the three other currents, all added together. So I2 plus I3 plus I4. That is equal to the current in the wire that we're looking for. Now, that's the magnitude of it. We already determined the direction, which is out of the page. So in a 3D graph, we have z-axis, we have the x-axis, or this is the y-axis, and then we have the x-axis that comes out of the page. So negative z is down, negative y is to the left, negative x is into the page, which means that our direction is in the positive x-axis or coming out of the page, whichever is easier to write. And that's the direction for I. This equation gives you the magnitude of I. And there you have it.